today is going to be like seriously afterglow heavy, right? So we're going to do basically everything on the computer. Basically going to be the same procedure 3 times, or similar procedure 3 times, except that we're basically building our distance ladder from the size of the Earth, right? That's what we did last time. We used the size of the Earth to get out to the next nearest star, right, out to Tauri. Now we're going to use, we're going to build on that to get even farther out, right? So we use these things called standard candles, and there are varying distances. You have RR Lyrae to get you to globular clusters in our own galaxy. You have Cepheids, which get you to nearby galaxies, and then you have Type 1a supernovae, which gets you way past them. Okay? So you're basically going to do one example of each one of these types of stars. Okay? So here we go. It's lab 5. So this is an introduction to the magnitude scale. So you guys all got that right. It's in reverse. So negative is actually brighter than positive. So it's just a little bit weird. It takes a little bit of getting used to, but it looked like most of y'all got it right on the quiz, so that's good. Now, what we're going to do in this lab is something called photometry. So what that does is you have some image of the sky, and you want to know how bright is a certain star in that image. Okay? So unfortunately, we can't just take what the computer gives us and say that is how bright the star is, right? Because conditions change from night to night. You may have some light cloud cover or something like that that's going to either increase or decrease the amount of light that you get for that star. And so then you're going to increase or decrease the magnitude that you read for that star. Okay? So what we have to do is compare it to a star that we know the magnitude of. Okay? So in this example, the first one is really simple. Okay, just load up one picture. You take use the photometry tool, which is this guy right here, the one with the double circle, and you click on uncalibrated magnitude of reference star. So you click on this one, it gives you a value, and then you click on that one, and it gives you a value. Okay, here's the load. Now we know the value of this one by other means is actually 12.01. Right, so it's there. So we can use that known value to figure out how much do conditions, let's say, affect this image. Okay, and then we can use that effect to correct our measurement, okay, to figure out what it actually is. Okay, do I follow? Okay, now this one is just a manual. You're gonna click on one and get the magnitude, and then you're gonna click on the other one and get the magnitude, and then you're gonna do the little math to correct it. Okay. And the little math is literally like a subtraction and an addition, so you guys can handle that. That's part A, okay? The next one is where the math gets a little bit more tricky now, and these are ones where, like, if you struggle with math, then just talk to me, right? Email me. I'm always willing to help you out with this part, okay? So the next part is all about standard candles, and that's what we're going to use to get farther and farther away, building our little distance ladder. Now, the problem in astronomy is, like, if you look at this picture here, you see the same thing for both of these stars, let's say, but you don't know if this is a bright star that's really far away and this is a faint star that's really close. You don't know. They all look the same. So what we have to do is figure out the distance to them. Okay? Now, these formulae right here are actually not that useful for you guys. So if you find yourself trying to use what you measure in this lab in these two formulas, then you're doing it wrong. Okay? These are just in here as background information. Everybody got that? So don't email me and say, I don't know what L is and I don't know what B is, so I can't solve this equation, because you don't need to know those two things. Okay? Because it's not the formula that we want to use. It's in here for background information. So this guy, on the other hand, is going to be your best friend. Okay? So that is the equation that you're going to want to use whenever you're trying to calculate this distance. Okay, now this is the only part that's tricky about this math-wise. It's just order of operations, right? So make sure you pay attention to that. You need to do the stuff in the exponent, and then you do the exponent, and then you do the 0.01. Okay? So don't get confused on that. There's another formula coming up. again, you just need to do it from inside the parentheses outwards, right? So that's the distance formula, okay? So here we go. These are the types of variable stars, okay? So you have RR Lyraes and Cepheids. RR Lyraes are quicker, so they vary on a quicker time scale. They're usually like less than a day. They change their brightness, but it's very regular, right? So so you can see this pattern if you were to stare at it for a constant 3 days. You would see this pattern. The problem is, it's kind of like what we did with the moon exercise. We can't stare at it for 3 days straight because we get daytime every 12 hours or so. So we might get this piece one night, and then we might get this piece the next night, and then we might get this piece the third night, etc., right? Forget what the bottom of the scale says. So we're going to get pieces and pieces of this over like a week or something. All this data is already collected for you, okay? So then what we're going to do is something called period folding, where we basically chop this x-axis into some set number. And so all of these things are going to line up on top of each other, and we'll be left with something that looks like this, where it's just one of these little guys that's going to be repeating over and over again. Okay? So it's the exact same principle with the Cepheid, except that the period is a lot longer. This doesn't really show you how long it is, but the Cepheid that we're going to look at has got some like 60-day period, so it's a really long time. And again, that data has already been collected for you. Okay? So, all right. So this is an important, everything that's bold in here is, I don't know if it's bold now on the new website or not, but it is. Okay, so this is bold. That means you read it. Same thing with this one, okay? Turned out that all RR Lyraes have about the same absolute magnitude. Okay, so absolute magnitude is what they are intrinsically, and apparent magnitude is what we measure them to. Does that make sense? So it apparently looks like whatever we measure, but it actually is absolute whatever. Okay, and that's the difference between big M and little m. Okay, so for anything that has to do with RR Lyrae, we use big M as 0.75. Okay, and anything that has to do with the Cepheid, it's not quite so easy, right? So again, we need to calculate it based on the period. Okay, so again, order of operations, there's a log here, everybody understand that log. There's a new button on your calculator, maybe you haven't pushed it in a while. You're going to get a chance to in this lab. Okay, so this is how you calculate the big M for a Cepheid. Okay, then you're going to measure the little m's. All the little m's you're going to measure. All the big m's you're going to calculate, or you just know it. For example, for the RR Lyrae, you just know what's up. Okay. All right. So then we move on to the farthest measurement that we can make, which is with supernovae. Okay. So when these things blow up, it turns out that they are very consistent, right? So these are the light curves. So what that means is if you measure the brightness of the object over time, in this case, like 200 days, the brightness increases and then it decreases, okay? And eventually it's going to decrease all the way, but these curves are very distinct, okay? And so that the shape of that curve tells you, whether it's a type 1 or a type 2. And so again, this data is given to you. So in the case of type 1 supernovae, big M is approximately negative 19.3. Okay, so again, there's another big M. Okay, so the big M's come from within the lab, and the little M's come from what you measure. Okay, so we're going to do the one for spring. Okay, 3201, that's the one we're working on. Moving on. Okay. So nearby galaxy, there's only one, so you can't get this one wrong. Okay, it's the same procedure, except you use the Cepheid formula for absolute magnitude instead of the RR Lyrae formula. Okay, and this one is the supernova. Okay, so there's a galaxy right here, this thing, and then this is the reference star. So the first thing that you're going to have to do is make a movie with these to figure out which one of these other dots is the supernova. Okay, because we don't tell you that, right? So when you run the movie, one of these stars, one of these guys somewhere in here is going to get brighter and then disappear, basically. Okay? And so once you figure out which one that is, then you can go on with the lab. Okay, that's the first step of the third part. What we're going to do now is I'm going to work through one of these little examples. Okay, so in this case, this is a new, let me turn off the light so you can see the thing better. This is a new feature in Astro that you haven't used before. Okay, so it's called batch photometry. So remember, in the first part of that lab, you do photometry, well, you do it manually, right? So you measure how bright the star is, and then you measure how bright the reference star is. And you do that manually. Now, if you wanted to do this the right way or whatever, you would do that on every image in the directory. Okay, because you want to see how it changes over time. Okay, but once you do it once, you're pretty solid on how to do it. So we just do it we let the computer do it for us. Okay, so we just click this one, click that one, and say go. All right. So we're going to go to process. That's batch photometer. Now let me just show you. Wrong one again. Okay. Panels. Okay, so which one of these are you guys doing for the RR Lyrae? 3201, perfect. Okay, so this is the ones you're going to do, right? Now, remember I just said, in the real, if you were going to do this by hand, you would have to figure out the magnitude of the star and the reference star in each one of these frames, right? That does not sound very fun. So in this case, you can just do it automatically with the afterglow batch photometry. Now, I'm not going to do this example because then I'll do your work for you. Nobody wants that, right? Okay, you might want it. You might want it, but I'm not going to. Okay, so I've already aligned a few of these images for the other one. So let me just bring it in. Okay. All right, so in this case, so the images that you're going to have WCS on them. That's called World Coordinate System, and it makes your life a whole lot easier. This does not have WCS, so I had to do things a little bit trickier. It's a little bit trickier to do. So what I'm going to do is first click on, first you want to have this thing open so you can figure out which one is your reference and which one is the RR Lyrae. Okay. So once you know that, in here, click on this one, let's say. Now you type in ref. So that one's the reference, and this one here is the RR. So type in RR. Make sure you do that right. Off of this one, go on to that one. Okay. Now you want, in your case, you want to have this use WCS clicked. Okay, then because that will find it in every image without having the things be aligned. Mine, I need to have them aligned, so I can't do that. So I say find all sources, or find these sources in all the images. So it goes through all these images and it looks for the sources. And if you switch the image, you'll see that the X's are still on the reference star and the RR. Okay, that's what you want to have happen. So now you do next, and what it's going to do is put out a table. In this table, it's going to have taken that photometry measurement of each of those two stars in every one of those pictures. Okay, so what you want to do after you have this table is go to Export, Data Analyzer, and then click on Variable Source. Okay, that's going to bring up this chart. Okay, so you pick the variable source, which is the RR, and you pick the reference, which is whatever you named them on the previous slide. Now, before you actually save this, you want to go ahead and put in the reference actual magnitude, so we do that right there. So let me get that. So. Okay, and now this is what our graph looks like. It's pretty convincing, right? No, right? We don't know what the hell is in this graph, right? So that's because we have different pieces of that function, right? Remember, we can't look at it for like 3 days straight. We have to look at it in pieces, okay? So we're going to use that technique called period folding, which is where you basically just cut the x-axis. Let's say that we made the period 1 day. So we would take this day here and the data that's in between and move it over here. Okay? And then we would take this one and move it over here, and we take this one and move it over here. So everything would be between 0 and 1. Okay? There's a little video tutorial on this. It's really helpful, so make sure you watch that. The first thing we want to do, we could just guess the period, but that's not going to be very effective because there's a huge range from 0 to 1 day, right? So what we're going to use instead is a technique called Fourier analysis, right? So we're going to switch over. Basically, you don't have to know anything about Fourier. You're just going to use it to get you a guess on what the period is. So you switch over to that. Now remember, I said RR Lyraes are between like let's say 0.1 and 1 days, and then now you just need to pick a step size, right? Sorry for that little brain part. And so now you're going to just pick a step size so that you can see the periods and their, what he labels as spectral power density. Okay, so again, you don't have to worry about what all that means. All you're trying to do is figure out which one of these is a peak, okay? And where does it line up? Okay. Now in this example, I have a very small amount of data because I had to chop it down because of a bunch of random factors. But so it's not as clear in this example as it will be in your 3201. Okay. So so between 0 and 1, where do you think the peak might be in this? Around 0.5, or what's another one that's really close to that? Right, so 0.3 something. Okay, now if you want to know what that is, you just use your mouse and hover over. So this is 0.33, this one is 0.49, let's say. Okay? Now it turns out that both of those look okay in this example because, again, I don't have enough data to differentiate between those two. But once you figure out what the peak is, right, it'll be, I promise you, it'll be much more clear in the one that you're doing because you have enough data to break this degeneracy. So once you know that period, right, so let's say that we're going to use 0.33, okay? So if we switch back over to the light curve view, and then check this box for period folding, and then put this as 0.33, okay? So now we have, if you can imagine this thing is going to repeat over and over again. Yeah, that's right. And if you put in 0.4, 495, they're similar, but in the other example it will be much clearer. We just need more data that's good data for this set. Okay? All of your plots will come out of this lab, not the other plotting tool. Everything comes out of here. So you just export and save it as a PNG file. And then just make sure that when you do that, you can change the name whatever you want, but just make sure you put .png on in. Okay, that way it will show up on your desktop and website of the plant you try to upload it. Okay. So any questions?
This is for doing the same thing for each.
Yep. Okay. Yep. You're going to batch photometer the RR Lyrae, which is in NGC 3201. You're going to batch photometer the Cepheid, and then you're going to batch photometer the supernova once you figure out which one is the supernova. Right? If you don't know which one of those dots is, it's not going to make the movie. Okay.